reflections, and stretches. A reflection of a graph creates a mirror image in a line called the line of reflection. Reflections, like translations, do not change the shape of the graph. However, unlike translations, reflections may change the orientation. When the output of a function y equals f of x is multiplied by -1, the result, y equals negative f of x, is a vertical reflection of the graph in the x-axis. Let's look at y. In this function, the negative is outside of the original function. If it's outside, that means that it affects the y value. So that means that each point, x, y, the x is not going to change, but each of the y values is going to become negative. So graphically, that means that if I have a point over here, right now the y value of that is positive, it's going to end up staying with the same x coordinate, but it's going to move down to a negative position. And so what's going to happen is the graph is going to flip vertically. The second situation is when the input of a function is multiplied by -1. The result, y equals f of negative x, is a horizontal reflection of the graph in the y-axis. So again, let's look at a mapping diagram. So each x and y and what happens to it. Because that negative sign is inside of our function, means that it's going to affect x. And so the x value is going to become negative, and the y value is not going to change. So if I look at that same point as in the previous example, this time the y value is not going to change, but the x value is going to go from negative to positive. Any negative x values will become positive. So in the first one, our graph flips this way, and in the second example, our graph flips this way. And so in the second one, it's called a horizontal reflection. In the next two examples, we have a function where we don't have the equation, we just have the graph of the function. And in part A, we have to graph y equals negative f of x. So if we start with our mapping diagram, this negative is outside. That means that it's going to affect the y value, and all of our y values are going to become negative. So if I do our key points, the first key point is -4, -4. I'm going to put these in the middle because we have the same graph for both of these. The second one is -2, -2. 2, -2. And the fourth key point in this picture is 4 and 2. I'm going to do my mapping this direction this time. So for part A, what's changing is the y value. The x does not change. So my x stays at -4, but instead of being -4 for the y, it becomes +4. The next point is -2, 2, 2, 2, and finally 4, -2. Let's graph it and see what happens. So -4, +4, -2, +2, 2 and 2, and 4 and -2. If I connect those points again, hoping that you can see that the blue graph is a reflection in this direction of that original function. We call this a vertical reflection. We can also say what it's being reflected around. So it's a vertical reflection about the x-axis. Let's look at part B. In part B, we're asked to graph f of -x. That means that this time, our mapping diagram, that negative sign doesn't affect the y, instead it affects the x values. So each of our key points then the x value changes signs and the y value stays the same. So we end up with 4 and negative 4, 2 and negative 2, negative 2, negative 2, and finally negative 4 and 2. Graphing those, 4, negative 4, 2, negative 2, negative 2, negative 2, and negative 4, 2. Let's connect them and see what we end up with. This time, our graphs are being reflected in this direction. Right? This point has moved over here. This point has been reflected this way. So we call this a horizontal reflection. About, and which axis did it flip around? So it's about the y-axis. Let's look at both of those graphs, and I want to look at what are called invariant points. Invariant points are points on our graph that don't change when they undergo a transformation. So in part A, the only point there that didn't change is this point. Because it was being reflected about the x-axis, any points that are on the x-axis won't move. So that invariant point is the point 3 and 0. On our second graph, the only point that didn't change is the point that actually lays on the y-axis. So we have several points that are in common, but that's the only one that doesn't move. That invariant point is the point 0 and negative 2. Compare the graphs, given the graph of y equals f of x, graph the functions y equals negative f of x and y equals f of negative x. How are the graphs related to the original function? Okay, so the same idea here. On this graph, let's do y equals negative f of x. And on this one, we will graph y equals f of negative x. Starting with our list of key points, and if I list those down the middle, I can use them for both graphs. Point A is at the point negative 4 and negative 3. B is at negative 2, negative 3. C is at 1 and 0. Point D is at 3, 4. And point E is at 5, negative 4. In this first one, the negative is outside, so it's going to affect the y value. So each xy is going to change to, the x is going to stay the same, but the y value is going to change signs. So let's do our new key points. X value stays the same, only the y value changes. We'll change each of those in the same manner. 0 and negative 0, so it stays still as 0, so it still stays as 1 and 0. 3, negative 4 now, and 5, negative 4. Plotting those points, positive 5. Sorry, I forgot to change the sign in the last one. It should be 5 and positive 4. 5, positive 4. 3 and negative 4. 1 and 0. Negative 2, 3. And negative 4, 3. If we connect those, there is our graph. So those points have moved in this direction. So we say that this is a vertical reflection about the x-axis. Okay, let's look at part B. This time we are graphing f of negative x. I'm going to try and move this out of the way for us. And so in our mapping diagram, what happens this time is the only change is to the x value and not the y value. So in each of these points, remember to be using your original points. The x value changes, so it's going to become positive 4, negative 3, positive 2, negative 3, negative 1, 0, negative 3, 4, and negative 5, negative 4. Graphing those, I start at the top, 4 and positive 3. Something doesn't look right there. Let's have another look at that. Sorry, 4 and negative 3. 4 and negative 3. 2 and negative 3. Negative 1, 0. Negative 3, positive 4. Need to move that up one. And negative 5, negative 4. And so our new graph looks like this. So which direction have those points moved? They have moved in this direction. And so this time we have a horizontal reflection about the y-axis. Now let's look at stretches. So we have horizontal and vertical stretch. A stretch, unlike a translation or a reflection, will change the shape of the graph. However, a stretch will not change the orientation. When the output of a function, y equals f of x, is multiplied by a constant a, the result is y equals a f of x, is a vertical stretch of the graph about the x-axis by a factor of the absolute value of a. When we're looking at stretches, we want to look not at the sign of a, but at just the absolute value of a. So let's look at an example. If I have y equals 2 f of x, our mapping diagram, that 2 is outside, so it affects y, so no change to the x. But what's going to happen is we're going to multiply each of those y values by 2. So any y values that are positive are going to move higher up on our graph. Any y values that are negative are going to move lower down. And so the effect is stretching it away from the x-axis. When we make a change to the input and multiply it by b, so that that multiplication takes place inside of our function, then what we are changing is the x value. But remember that x does exactly the opposite. So let's give us a number example here. If we have y equals f of 2x, the 2 is inside the function, so it affects x, but it's going to do the opposite. So instead of multiplying by 2, we are going to divide by 2. That's where this 1 over the absolute value of b comes from. Remember, we're only worried about the absolute value of a and b because we're already going to think about those negatives in terms of a reflection rather than a stretch. Let's look at an example. So here we're asked to graph y equals 2 f of x. That 2 is outside of the function, so that means that it's going to affect y, and so we're going to end up with this as our mapping. Making a list again of our key points, negative 4, negative 4, negative 2, negative 2, 2, negative 2, and 4, 2. Our mapping diagram says to not change the x value, but to multiply the y value by 2. So negative 4 times 2 is negative 8. Negative 2 times 2 is negative 4. Negative 2 times 2 is negative 4. And 2 times 2 is positive 4. Let's look at what happens to our graph. So negative 4, negative 8, negative 2, negative 4, 2, negative 4, and 4, 4. Here's what our new graph looks like. So it's changed shape because all of the points above the x-axis get pulled further away from the x-axis. All of our points below the x-axis get stretched further away. So this is called a vertical stretch about the x-axis. We also want to describe how much it's been stretched. So it's about the x-axis by a factor of, what did we multiply our y values by? 2. Let's look at a horizontal stretch. So in this case, R2 is inside of the function, so we know that it's going to affect the x values. And it's going to do the opposite. So instead of multiplying each of our x values by 2, it's going to divide each of them by 2. There's no change to the y values. Listing our key points. We can now finish our key points in our mapping. We're going to divide each x by 2, so this becomes negative 2, 4, negative 1, 4. Let's try that point again. Negative 2 divided by 2 is negative 1, no change to the y. 2 divided by 2 is 1, no change to the y. 4 divided by 2 is 2, no change to the y. So let's look at what our picture looks like. Negative 2, this should be a negative 4. Negative 2, negative 4. Negative 1, negative 2. 1, negative 2. And 2, positive 2. If we connect our points, I hope you can see what's happened is we've squished everything closer to the y-axis. Even though we've squished it, we're going to describe it as being a stretch. So the movement has been that everything has got moved towards that y-axis. So it's going to be a horizontal stretch about the y-axis. That's the one that we're moving towards or away from, by a factor of, what did we multiply each of those x values by? Well, we divided by 2, which is the same thing as multiplying by 1/2. I want to look at some additional information for this graph. So once again, let's talk about those invariant points. Invariant points are points that don't move after the transformation. Well, the only point on this graph that wouldn't move is the one that happens to be exactly on the y-axis. So our invariant point is the point 0 and negative 2. I'd also like to look at the domain and the range of both functions. Let's start with our original function. So the domain of our original function was all x values between here and here. So all x values between -4 and +4. If we're using interval notation, we're using square brackets because -4 and +4 are actually included. The range of our original function, so what numbers can y be? The lowest value is -4. The highest value is up here at +2. If we look at the domain and range of our new function, when we did this one, the only thing that we changed were the x values. So that means our domain has to change. Our domain now has become half of, because we've divided those values by 2. So they are going to go from -2 to +2, which you can either look at your graph to figure out, or you can make those same transformations on the domain values. The range, we made no changes to our y values, so it should stay at -4, +2. The last piece of today's lesson is being able to write the equation of the transformed graph given the two original graphs. It says graph the function that has been transformed by either a stretch or a reflection and write the equation of the transformed graph. In part A, the shape of our graph has changed, therefore it's not a reflection but a stretch. Right? Remember that reflections can't change the shape, only stretches can. This stretch could have taken place either horizontally or vertically, and in fact with this graph we can look at it both ways. So let's first of all look at what happens if we assume that this has a horizontal stretch. A horizontal stretch means that those points have moved in this direction, either in or out. To do that, we're going to look at how those points have changed. So we're going to pick 2 points on our original function that have the same y value, and we're going to look at how the width between those, or the distance between those 2 points, compared to the distance between the similar points on our new graph. Now I didn't pick very good points there, so let's change that a little bit. Instead of looking at those, let's pick points up here. And the reason that I've done that is because I wanted to compare them to the same y value points on our new graph, and the other ones weren't at corners of squares, and so it was hard to estimate the value. So if we look at the distance between the 2 blue dots on our original graph, that distance is 6 units. When it's been changed onto our red graph, the distance between those is now only 2. So what did we do to those points? Well, we divided those by 3 or multiplied by 1/3. What we would multiply by to go from the blue to the red would be our stretch factor. So this is a horizontal stretch by a factor of 1/3. If we have a horizontal stretch by a factor of 1/3, what's being changed are those x values. So that means that each point in our original function had the x values multiplied by 1/3, but no change to the y. As an equation, if our original function is absolute value x, this 1/3 has to take place inside of the function, and it's going to do the opposite. So instead of dividing by 3, we are going to multiply by 3, and there's no change to the y value. Now let's do the same thing, but this time let's look at it as though it were undergoing a vertical stretch. So this time we want to pick 2 points on and look at them vertically. So what I'm going to do is look at the point, I'm going to use the same point, but I'm going to look at the distance between that and the x-axis. So the original distance was 3. After the transformation, it went from here down to the x-axis, and so that value is 18. So it moves from 3 to 18. That means that we multiplied by 6. Sorry, I misread my graph. This first distance isn't actually 3 because my graph is not going up by 1. That first distance is actually 6. The second point is now up at 18. So now I've got my change correct. So what happens from 6 to 18 is we've multiplied by 3. If it's a vertical stretch, that means my mapping this time is something that happens to the y values. So the x values stay the same. The y value has to get multiplied by 3. So as an equation, we end up with y equals, our base function was absolute value of x. The 3 changes the y, so it has to happen outside of the original function. And we end up with y equals 3 absolute x. Well, how can two different equations represent the same graph? If we compare y equals the absolute value of 3x with y equals the absolute value, 3 absolute value x. 3 is always going to be positive, so these two equations are actually equivalent. Both of them can be written as y equals 3 absolute value x or y equals the absolute value of 3. One last example for today, same idea, this is part B. This one, the shape of the graph hasn't changed, but what's changed is the orientation. So it's gone from opening up to opening down. If we look at our mapping diagram then, each of these x values has gone from here to here. Sorry, the y values are what has changed. So our x hasn't changed, but the y now has become negative. Our original function is the absolute value of x. If it's the y that has become negative, that means that that negative has to take place outside of the original function, and our new function is y equals negative absolute value of x.